At the other end of the spectrum, there is insatiable demand for more performance. Absolutely incredible demand. Just a simple example. In medical imaging today, many people will, if they're unfortunate enough to be ill, you will have a CT scan where they take many, many slices of images inside your body. And then they have to put those together so that it is something coherent that you can examine in order to see whether you have something wrong. Today, that scan, up to this current environment, takes about 2.5 hours to compute. Within the next 2 years, that will be 6 minutes. Now, it's not just, isn't that convenient, it's 6 minutes. It means today, you go and have a scan and you go away. And you come back 2 weeks later and they schedule an appointment. And instead of that, you will have the scan. The doctor will say, would you like a cup of tea? You'll have a chat for 2 minutes and out will come your scan. Think about the change that brings. Another example is today we have an error of, for example, looking at weather, we have an error of about 111 miles on a hurricane. Now, being able to track where it's going to go, we can get to within 100 miles either way. That, by the way, is 3 times better than it was a decade ago, so that's good. But if you're 50 miles away from where you think it's going to go, 111 miles isn't very comforting. You'd really like to know a little better whether it's going to hit you. To get to the point where you can compute 2 weeks of weather and track accurately on a hurricane requires a zettaflop. Now that's 10 to the 21st, so you can figure out it'll take you 5 minutes to write it, but it's a very big number, and that is probably going to happen in the next 20 years. So you can see we're moving forward at a very rapid pace, but there's still much, much more to happen. And this is also really exciting because the first comment about crisis being opportunity applies to the biggest crisis of all, what is happening to our planet. And if you look at what's happening to our planet, global cooling is also an opportunity for us to reinvent industries and businesses to be cleaner and smarter. And that takes smart people doing that. Some examples of that are manufacturing, construction, transportation, connectivity. All of these have the opportunity to move to be much greener, to be much smarter, and much more effective. If we look at one example here is applying this to design and simulation. Today, top performing manufacturers build half the number of physical prototypes. They get product to market 58 days faster. They have 48% lower prototyping costs. These are incredible changes, and the Xeon 5500 is going to help people do this much more intelligently. And this applies across the board to this industry. So moving your manufacturing to true simulation. Simple example, cars. Cars today are simulated. Okay, we work very closely with most of the Formula One teams to simulate that so they don't have to put them into wind tunnels and spend all that money building models that don't work. At the same time, today we don't have enough compute capacity to simulate what happens to the human being inside the car when it stops. I mean, really stops, as it hits a wall. In that environment, you need significantly more, probably in the area of an exaflop, to start simulating the effect on the human being and not needing to have those dummies, you know, the funny ones that keep hitting walls. That would be a remarkable change, but it's an example of where computing is used. Likewise, if we look at smarter construction, US buildings represent 71% of the total energy consumed. So we can blame airplanes and cars, but buildings are a much bigger part of this. 39% of energy consumption, 39% of CO2, 36% of greenhouse gases. Using 3D to actually simulate buildings, to understand traffic flows, airflow, understand how to minimize the use of materials will cause a revolution, and it is causing a revolution because the value of this sector has moved from 10 billion in 2005 to 49 billion in 2008, and it could triple by 2013. An area, by the way, where Sweden has been a leader in many areas of construction of homes, for example. Making them smarter is going to be a big deal for the economy. The next area, smarter transportation. What you see here is the Chinese rail network. Now, it's got some small numbers on it. $330 billion invested, with 3.2 passengers a year, 63,000 trains, carriages, 25,000 miles of high-speed track, 350 kilometers per hour maximum speed and 6,000 stations. Now, I don't think it takes a genius to realize doing this without computers would be tough. Not only in designing this network, understanding how it interoperates, understanding what is needed, but also designing the cars to be efficient, the train cars, designing the track to be the most efficient to ensure that you're losing the least amount of energy in that process. Those are all critical to us. The final area that I'll mention is the grid itself, power and energy. We waste significant amounts of power today because our grid is dumb. Moving that to an intelligent grid where you know how much energy you're expending, where your refrigerator knows to turn off its defrost cycle when the peaks of power are happening, where your dryer reduces its temperature by 5 degrees, which doesn't really matter, but saves a few gigawatts when you add them all up. Moving to that intelligent grid is something that is absolutely mandatory in the next 10 years because the current grid can't, for example, handle all of our renewable energy. So many areas where new industries are going to be formed that need every bit of computing power we bring to them. So that gets to what we're bringing to them. An intelligent platform, a very adaptable platform that's been designed specifically for those challenges. So if we look at this, it's based around the 45 nanometer high K processor with intelligent performance, which means when it needs to be more highly performing, it increases its performance. When it doesn't, it reduces its energy. So it's extremely efficient, it's flexible, it brings in new forms of virtualization, and it's very dynamically scalable, so I can create very large clusters out of that. Some examples here. It automatically puts the CPU into the lowest available power state while still meeting its performance requirements. So it realizes what's needed from it and lowers the power. But when it's required to do more power, it can add up to 400 megahertz of performance to its rating for a short period of time to take care of the peaks. So if you're building computers today or you're using computers, you will buy extra ones just in case there's this period where you have a peak. This computer will actually take care of that peak without buying another computer. This is a major change. When we look at the design criteria in this, you're really looking for scalability in a way that is very difficult to achieve in most fields. So for example, if we were building an airplane, we would want it to be as fast as a fighter jet. We want it to carry the capacity of an A380 or A340, a big jumbo jet, and we'd like it to have the fuel efficiency of a glider. Right? Nothing much to ask. Very difficult to achieve, but it's exactly what we've achieved with this Xeon 5500. So it is not exaggeration to say this is the largest increase in performance we have offered ever on Intel servers. It is an enormous change to the environment. It's an enormous change that allows us to minimize cost, which is very important in the current environment, while at the same time meeting people's performance requirements. The idle power is less than half of what the current generation is. And if we look at this comparing to even computers from about 18 months ago, you see a 5x improvement in switching speed, a 5x improvement in idle power. I mean, major, major changes to that. And it's not just that it runs faster. It does that out of the box without any changes, no need to do anything. But we've also had thousands of engineers working with companies in the software business to ensure that their software is optimized for this environment, because we do have a major change happening here to multi-core computing. A major change where people have to think about how to spread loads across lots of different cores. And over 30 real-world applications today seeing 2 to 3 times the performance of the last generation. So a very rapid change indeed.